For nearly all forms of life on Earth, there are strict boundaries. Beyond a certain temperature, pressure, or level of hydration, biological systems simply cease to function. Our understanding of living things is often defined by these delicate thresholds. Yet, nestled within the mosses and lichens, in the deepest oceans, and even on the highest mountains, exists a creature that defies these established limits. It's a tiny marvel, smaller than a grain of sand, yet it possesses a resilience that borders on the mythical. This is the tardigrade, a creature built to endure the unimaginable, surviving conditions that would spell instant annihilation for almost any other living thing. Known affectionately as water bears or moss piglets, tardigrades are invertebrates ranging from 0.05 to 1.2 millimeters in length. Their plump, segmented bodies and 8 stubby legs, each ending in claws, give them a distinctive appearance under the microscope. While seemingly unassuming, these minute beings hold the keys to some of life's most profound mysteries. They are found across the globe, from polar ice caps to tropical rainforests, suggesting an adaptability that far surpasses their diminutive size. Their ubiquity is a testament to their extraordinary capacity for survival, a testament we will now begin to unravel. One of the most astonishing abilities of the tardigrade is its capacity to survive extreme desiccation, the complete absence of water. For nearly all biological organisms, water is life. Its removal means cellular collapse and death. Yet, tardigrades can lose up to 99% of their body water and remain viable for decades. This remarkable feat is achieved through a process called anhydrobiosis, where the tardigrade enters a state of suspended animation. It retracts its head and limbs, shriveling into a compact, barrel-shaped form known as a tun. In this state, it effectively pauses life, waiting for conditions to improve. How does a cell survive without water, when water is essential for maintaining structure and function? The secret lies in a special sugar, trehalose. As the tardigrade dries out, trehalose floods its cells, forming a glassy, protective matrix. This sugar replaces the water molecules, preventing crucial cellular components like proteins and membranes from denaturing or breaking down. It acts as a molecular scaffold, preserving the integrity of the cell until water becomes available again. Without this ingenious mechanism, the delicate machinery of life within the tardigrade would be irreparably damaged by desiccation. Beyond desiccation, tardigrades exhibit an astonishing tolerance for extreme temperatures. They have been revived after being frozen to temperatures as low as -272 degrees Celsius, just 1 degree above absolute zero. At the other end of the spectrum, they can withstand scorching heat up to 150 degrees Celsius for short periods. For most animals, such thermal shock would instantly destroy cell membranes, denature proteins, and cause irreversible damage. The tardigrade, however, employs its cryptobiotic state to enter a protective dormancy, allowing it to weather these incredible thermal fluctuations without harm. Perhaps the most dramatic demonstration of tardigrade resilience occurred when they were launched into the vacuum of outer space. In 2007, a European Space Agency mission exposed active and desiccated tardigrades to the full fury of the space environment, vacuum, intense solar radiation, and cosmic rays. Most specimens in the desiccated state survived, with some even reproducing successfully upon their return to Earth. This incredible feat highlights their unparalleled ability to protect their internal systems from the profound cellular damage caused by radiation and the sudden, complete absence of atmospheric pressure. The vacuum of space includes a bombardment of lethal radiation. Tardigrades can withstand doses of radiation hundreds to thousands of times higher than the lethal dose for humans. This extraordinary resistance was a puzzle for decades, until scientists discovered a unique protein named SUP, short for damage suppressor. SUP protein binds to the tardigrade's DNA, forming a protective shield that minimizes radiation-induced damage. It acts like a molecular bodyguard, safeguarding the genetic blueprint of the organism from degradation, a defense mechanism unparalleled in the animal kingdom and crucial for their survival in extreme environments. The SUP protein is more than just a shield, it actively contributes to DNA repair mechanisms within the tardigrade. When radiation inevitably causes some damage, SUP facilitates the efficient and rapid repair of broken DNA strands, preventing mutations that would otherwise be lethal. This dual action, protection and repair, is fundamental to the tardigrades' radiation resilience. Without SUP, their survival in conditions like outer space or highly radioactive environments would be impossible. It's a testament to the intricate biological solutions that allow life to persist in the most unforgiving corners of existence. The deepest parts of our oceans experience crushing pressures, thousands of times greater than its sea level. Even in these abyssal depths, tardigrades have been found. Experiments have shown they can survive pressures of up to 6,000 atmospheres, a force equivalent to an elephant balancing on a thumbnail. For most organisms, such pressure would collapse cell membranes, denature proteins, and disrupt all cellular processes. The specific mechanisms allowing tardigrades to withstand such forces are still under active investigation, but it's clear their cellular architecture and protective strategies play a vital role in preventing catastrophic collapse. When faced with any of these life-threatening conditions, desiccation, extreme heat or cold, vacuum, or radiation, the tardigrade can enter a state of cryptobiosis. This isn't mere hibernation, it's a profound suspension of metabolic activity, where life processes slow to an almost imperceptible crawl. The tardigrade can remain in this state for years, sometimes decades, waiting for favorable conditions to return. Upon rehydration or stabilization of the environment, it can reanimate, often within minutes or hours, resuming its normal activities as if no time had passed. It's truly a masterclass in pausing life itself. The longevity of the tardigrade's cryptobiotic state is astounding. There are confirmed reports of tardigrades being revived after spending over 3 decades in a desiccated, frozen state. Imagine pausing your existence for 30 years, only to reawaken and continue as if nothing happened. This incredible endurance and suspended animation allows tardigrades to travel through time in a biological sense, bridging long periods of environmental adversity. This capability is not just a curiosity, it offers profound insights into how biological systems can be preserved, potentially informing advancements in cryogenics and long-term storage of biological materials. Beyond specific proteins and sugars, the tardigrade's overall cellular machinery is finely tuned for survival and repair. When it emerges from cryptobiosis, its cells quickly reactivate, repairing any minor damage that might have accumulated during dormancy. This rapid return to homeostasis, the stable internal environment of the organism, is critical. Mechanisms for detoxification, protein refolding, and membrane repair are all highly efficient. The speed and effectiveness of these processes ensure that the tardigrade can swiftly recover and resume normal metabolic functions, maintaining its extraordinary ability to thrive where others perish. While often less emphasized than temperature or desiccation, tardigrades also demonstrate considerable tolerance to extreme shifts in acidity and alkalinity, or pH levels. They have been observed to survive in highly acidic environments, down to pH 1, and highly alkaline conditions, up to pH 13. For most life, maintaining a stable internal pH is crucial for enzyme function and cellular integrity. Deviations can lead to rapid cellular death. The tardigrade's ability to cope with such chemically hostile environments further underscores its profound capacity to regulate its internal biochemistry and protect its sensitive cellular components. In conditions of anoxia, the complete absence of oxygen, most complex life forms would quickly perish. Yet, tardigrades have been observed to survive prolonged periods without oxygen, another testament to their adaptable metabolism. While they typically require oxygen for active life, their ability to enter cryptobiosis or a related anoxic diapause allows them to shut down their metabolic needs and endure. This capability is vital for survival in environments like waterlogged soils or deep sediments where oxygen becomes scarce, adding another layer to their incredible repertoire of resilience strategies. Let's revisit the ton formation, a deceptively simple yet critical aspect of tardigrade survival. When conditions become adverse, the tardigrade rapidly retracts its head and all 8 legs, effectively pulling its body into a compact, protective ball. The cuticle, its tough outer skin, becomes a resilient outer shell. This physical contraction minimizes surface area, reducing water loss during desiccation and creating a tighter, more robust form that is less susceptible to physical damage. It's a fundamental step in initiating the cryptobiotic state, preparing the internal cellular machinery for the protective measures that follow. The tardigrade's extraordinary resilience holds profound implications, particularly for the field of astrobiology. If life can survive such incredible extremes on Earth, what does that mean for the potential for life elsewhere in the universe? The discovery of their ability to withstand the vacuum and radiation of space directly informs our search for extraterrestrial life, suggesting that life might exist in environments previously thought to be uninhabitable. Tardigrades serve as a powerful reminder that the boundaries of life are far broader and more astonishing than we once conceived, challenging our very definitions of survivability. In summary, the tardigrade's arsenal of survival strategies is truly remarkable. From the formation of a protective ton to the molecular shield of trihulose and the DNA-guarding subprotein, every mechanism works in concert to ensure its persistence. Whether facing extreme dehydration, freezing cold, scorching heat, crushing pressures, deadly radiation, or the vacuum of space, these tiny creatures possess an inherent biological fortitude that allows them to simply pause life and wait. They are living proof that even the smallest organisms can contain the most profound secrets of survival, offering a masterclass in resilience and tenacity. The story of the tardigrade is far from over. Scientists continue to uncover new facets of their incredible biology, each discovery deepening our understanding of life's potential. These humble water bears remind us that adaptability and perseverance are cornerstones of existence, enabling life to flourish against seemingly impossible odds. Their enduring legacy is not just one of survival, but one of inspiration, a testament to the ingenious ways life can persist and thrive, even in the most inhospitable corners of our world and potentially beyond. The tardigrade stands as an ultimate symbol of uncompromising resilience, teaching us that there are indeed creatures that refuse to be killed.